Alright, this is lecture 12, and from now on we are going to move into the circuit design. And the simplest circuit we can design is this CMOS inverter. And this is a reference chapter from the Cedra Smith textbook. And the recorded materials from last spring and Professor Asif Khan. So what is a CMOS inverter? First of all, inverter. This is a building block in the digital circuits, and I believe in your 2020 you have learned the symbol like this. You have a triangle, and then you have a circle. Then this is a digital function to invert the input signal and output signal. So basically the truth table. If input is digital 0, output is digital 1, or if input is digital 1, output is digital 0. So this is a logic, but you have to implement that into the actual transistors on the silicon. So the simplest way to do that is to use this CMOS inverter. And you have NMOS and PMOS. So we have to do some wiring to connect the NMOS and PMOS to make this inverter. So first of all, the NMOS, lower potential is the source. So this is source, this is the gate, this is the drain. And for the PMOS, higher potential is the source. So this is source to the power supply VDD and the gate. So here, first of all, the input voltage is applied to the gate of both NMOS and PMOS transistor. So the gate of those two are connected together through this wire, and this is the input. And output is from the drain. So the NMOS and PMOS drains are connected together, and then you have wire to represent the output voltage. So in the analog domain, then you look for the voltage levels. So if input voltage is ground, then the output voltage will be the power supply VDD. Or if input is VDD, then output is 0. So that is the operation of this CMOS inverter to the very high level. So this is the actual implementation of this logic. And you have seen logic in 2020, but now from 3030, you need to implement that with the transistors, because in the real chip, then the logic functions are always implemented with those transistors. So the circuit symbol of the CMOS inverter is like this. And then if you look at the actual device structure, if you make that onto the silicon, then you have this kind of cross-sectional view of the NMOS and PMOS. So you have seen this kind of a structure in the previous lecture 11. So here the substrate is the p-type doping, so you can make the NMOS on top of that directly. And then for the PMOS, you have to first build this N-well, N-type doping, this N-well, and then make the PMOS in this N-well region. And then you have to use some interconnect metals to wire those terminals, like the two gates are connected together. So you need to use this wire here to connect those two gates. And if you recall lecture 2, this is a metal interconnect. We have those so many layers of the metal interconnect. And for those neighboring cells, we just use the lowest level, like metal 1, and make the interconnect between those two gates. And then the drain of those two NMOS and PMOS will be collected as an output voltage. So here we just want to say a few more words on the body. So here this is a body terminal for the NMOS, and it's attached to the source here. So in the real implementations, so the NMOS will have the source here, and the body is here. And the body needs to make a contact. So the body contact will be P+ doping in this NMOS case. And then these two will be connected together. It's like those two are connected together here. So similarly for the PMOS, the body of PMOS is typically attached to the source of PMOS together to the power supply VDD. So that's why here we have the PMOS source and the body for the PMOS, which is N-type. And we make N plus heavily dope to make a good contact, because heavily dope means lower resistivity. Then we can make a good contact between the silicon and the metal. So those are metal wires. So this is a cross-sectional view of the CMOS inverter. Any questions? All right, then let's look at the top view of the CMOS inverter. That is look from the top to the wafer. And this is called the layout. Basically, it defines the geometry dimensions of those NMOS and PMOS regions. So here, let's look at this layout in more details. So first of all, the PMOS needs to be built in the N well. So here, this gray shaded region is this N well. You need to define this region as N-type doping. So you need to define the boundary of those N well. And then the input voltage, here you have a contact. And this is the input voltage. And then you have the wire, this red one, those are the metal interconnect. And then you attach to the NMOS and PMOS. So the input is applied to the gate. So this was the circuit symbols here, circuit schematic. So then you can correlate the circuit schematic to this physical layout. So the input voltage, right, and then this output voltage. VDD and ground. So here we are looking at the input, that is here, this VO. This input is applied to the gate of those two transistors. So that means here you have this red line, those are the gates. So here you will have the gate here. This is the gate area. And the dimensions, like here, this one will be the L of the channel, and then this one will be the W, the width. So this is the drain, and this will be the source. So this is like this is the drain, this is the source for the PMOS. And similarly, this is the drain for the NMOS, source for the NMOS. So this is the drain and this is the source. So those two drains connected together. That's why here you have this blue bridge to connect those two contacts together as the output. Sorry, this is V in VI, and this is VO. So then this is a body contact. Body contact. That is this body contact here, and body contact here. So basically, this is one-to-one mapping from the circuit schematic to the physical layout. And also here we have the ground and the power supply. So here we have a ground line, which is much wider than the other interconnect here, and also have a power line here. The reason is that the power supply and the ground need to provide large current to many circuits. So here we only have one circuit here, but if you imagine there are many digital circuits, then the power line needs to deliver the power or the current to many circuits. So it has to be wider to carry those currents. So those are the power line and the ground line. And here in the middle, we have this layout for this circuit. This is from the top view. And this layout will follow the design rule. So the design rule basically will determine what is the distance. For example, between the power line and this N wheel, there are some distance here. And also what is the minimal L you can use, and what is the minimal contact size you can use. So those are limited by this design rule. And for different technology nodes, you will have different design rules. And in general, if you change from, let's say, 22 nanometer load to today's like 7 nanometer load, then those design rule will shrink the dimensions here. So that will enable your scaling of the chip. So this design rule is limited by the fabrication, like the resolution of your lithography, for example. So this is to be followed when you design the layouts. And as a circuit designer, your final job is to deliver this layout. So as a circuit designer, you are going to start with this kind of circuit schematic, and then you need to eventually implement that into this physical layout. So circuit designer, I mean, if you are working for Apple, for Qualcomm, those design house, then your job is to design the circuit and then draw this kind of layout. But today, there's a software design automation tool to help you automatically translate the circuit schematic to this physical layout following the design rule. And your final job is to have a file of this layout, and then you send this file to the foundry, for example TSMC, and then TSMC will follow your design rule, your layouts, to fabricate the real chip. So they will follow the dimensions here and then make the metals like this white and dope this region. So then they will make the process exactly the same as your design here. So that is how the processor is designed and fabricated. So this layout is the file between the design company to the manufacturing companies. And we are not going to discuss more details about the layout in this 3030. And if you are interested in this, you can take the more advanced VLSI system class. I think it's in the 400 level, and that will tell you how to implement the circuit from the schematic to the layout. And you have to use a software tool to do that, and that can be part of the lab project. All right, so I think time is up for today. And any final questions? If not, then we will stop here.